Hi, my name is Steve Blyle and I'm a welder. Wire feed, in one form or another, has become the standard of the welding industry. And with the development of less expensive welding machines, it's now common in all types of repair shops, on farms and ranches, and even in home shops. There are quite a few different manual and automatic wire feed processes. We'll be looking at gas metal arc welding, which is often referred to as MIG. This process uses a continuous solid wire along with an externally furnished shielding gas that protects the molten weld metal from coming in contact with the surrounding air. The weld puddle and weld buildup are very controllable and the finished weld bead is virtually slag-free. This process was first used in industry around the mid-1940s to speed up the production welding of heavy aluminum plate. A solid metal wire was used with an inert shielding gas, either argon or helium. This was referred to as MIG for metal inert gas. The characteristics of the inert shielding gases did not work well for welding on carbon steel, and this process did not become widespread until new wires were developed and used with either carbon dioxide or a carbon dioxide-argon blend. Because carbon dioxide is not an inert gas, the term MIG is technically incorrect. Everybody still uses it. MIG welding is a very familiar term, but the American Welding Society has designated this as the gas metal arc welding process to include all types of solid wire and shielding gases. Now, wire feed welding does have the reputation for being real easy. It might be a little more accurate to say that it's easy to get started. In any type of electric arc welding, the distance that the arc travels between the electrode and the metal, called the arc gap, is extremely important. With wire feed, when the voltage and wire speed are set correctly, the welding machine automatically maintains a constant arc gap, even with slight variations in the position of the wire feed gun. You can make a weld the very first time you pull the trigger, but there's more to joining metal than just squirting weld. This is considered a manual wire feed process. Even though the welding equipment does maintain the arc, feed the wire, and supply the shielding gas, the welder still needs to control the position of the wire feed gun, the direction of the weld, and the speed of travel. There's also metal preparation and joint fit up. Some of this is technical information and some deals with welder skill. While there isn't anything that's especially difficult or complex, the more you learn both about the welding part of it and the technical aspects, the more efficient and effective you'll be, whether you're headed into the welding industry or out into your garage. A typical wire feed welding setup consists of a power source, wire feed unit, the gun assembly, a ground connection, and a high-pressure bottle with a flow meter. This is considered an all-in-one machine. The power source and wire feed unit are combined. In industry, where more powerful equipment is used, the wire feed unit may be separate from the power source. Regardless of the type, size, or brand name, these machines all do the same thing: provide current, feed wire, and regulate the gas flow. So basically, they all have the same parts. Wire feed welding machines use a constant voltage direct current power source. This particular machine uses a transformer rectifier to change alternating current from the wall outlet into direct current that's supplied to the welding wire. With DC power, the direction that the current flows, called polarity, is determined by how the leads are connected to the terminals. Welding wires are designed to run on a specific polarity, and all the common wires for welding on carbon steel use direct current electrode positive, with the lead to the welding wire, which is the electrode, attached to the positive terminal. Wire feed also uses a CV, or constant voltage power source. This is different from a stick rod welding machine, which uses constant current. While you're welding, the voltage and amperage are always readjusting to keep the arc going. In wire feed, this mainly happens when the gun is held closer or further away from the metal. A constant voltage power source tries to maintain the voltage, with the amperage varying to provide the current necessary to burn off the wire and maintain the arc. CV power sources stabilize quickly, allowing the drive rolls to feed the wire at a constant speed. The whole wire feed unit itself is fairly simple. There's a spindle to hold the roll of wire, with a catch that's inserted into the back of the spool. The spring-loaded nut at the end of the spindle is tightened just enough so the spool stops when the drive rolls stop and it doesn't continue for momentum. The wire should come off relatively straight through a guide that keeps it centered in the grooves on the drive rolls and into a steel liner that's inside the gun assembly. Drive rolls are designed for specific wire sizes that should be indicated on the side of the roll. When you close the drive rolls, just tighten them enough to keep the wire from slipping. Besides the steel liner, the gun assembly also contains a hose for the shielding gas, a welding lead supplying current to the contact tip where the welding wire is energized, and control wires attached to the trigger. At the end of the gun, you have an insulator, an adapter, the contact tip, and the nozzle. Contact tips come in different sizes to match the wire diameter and also in different lengths. For gas metal arc welding, the contact tip should be nearly flush with the end of the nozzle. When you're installing a new roll of wire, after it's inserted into the liner and the drive rolls are closed, lower the hood, turn the machine on, and straighten the lead up a little. Then pull the trigger. There is a very close tolerance between the wire diameter and the opening in the contact tip. It's a good idea to have the nozzle and the tip removed until the wire is all the way through. Last is the shielding gas bottle and flow meter. This is a high pressure bottle and can be filled to over 2,000 pounds per square inch. You need to protect the cylinder valve from getting damaged. When the bottle's in use, it needs to be chained up securely. And when it's not in use or you intend to move the bottle, always use the protective valve cover, even if the bottle's empty. The flow meter regulates the amount of gas flow, measured in cubic feet per hour. Several styles are available, with the high pressure gauge indicating the pressure inside the bottle and the other gauge used to adjust the flow of gas. To open the bottle, get in the habit of standing back behind the valve, just in case something does come apart. Crack the valve slowly, then open it all the way. High pressure valves have two seats, one to close the bottle and the other to seal the valve stem when the bottle is open. So open the valve all the way. Regardless of the style of flow meter you're using, you get a more accurate adjustment with the gas flowing. So pull the trigger on the gun. Ideally, you want to use the minimum amount of gas that it takes to cover the molten weld, usually around 20 cubic feet per hour. Excessive gas flow may have a cooling effect on the weld puddle, and if there's not enough gas coverage or you lose the shielding gas for some reason, gas pockets called porosity will form in the weld bead. With the flow meter set, snip off the excess wire and you're ready to do some welding. This is industrial equipment, and even the smaller welding machines are well built, but part of wire feed welding is keeping the wire feeding smoothly. Let's go back through and take a look at some of the things you need to pay attention to. While you're welding, little bits of hot metal called weld spatter fly out of the molten puddle. Regularly check the nozzle and clean out any buildup of that weld spatter. There are anti-spatter products available, either a dip or a spray. These don't stop the spatter, just help to keep it from sticking. You want to make sure you don't have any weld spatter on the end of the contact tip too. If that heats up, it expands and pinches the wire, causing it to feed erratically. The wire can also burn back, sticking at the tip. This generally happens when you're starting the arc, especially if you're in an awkward position or the metal isn't clean. It's a good idea to keep a few extra contact tips on hand. The nozzle will either push on or screw on, but it needs to fit snugly. If it loosens up, you may have to replace the insulator. As clean and shiny as the wire looks, it still causes dust from the shop to gum up the liner, right where the wire goes in. This can build up enough to stop the wire from feeding consistently. Installing a wiper with some cleaner seems to help keep everything operating smoothly. It is extremely difficult to make a good weld when the wire is not feeding correctly. Generally, any problems will not be equipment failure, but rather some kind of contamination, either dirt buildup or weld spatter. Take the time to keep everything clean and in good working condition. With the increased use of gas metal arc welding, many filler wires and shielding gas blends have been developed. Keep in mind, only in recent years, with the introduction of smaller welding machines, has this process become popular for general purpose welding. It was originally developed and is used extensively to increase the speed of industrial welding, and you'll find that most of the gases and wires are used for high-speed production. Of the filler wires available for welding on carbon steel, the most commonly used is ER70S6. All these wires have a 70,000 pound per square inch tensile strength, indicated by the 70. Tensile strength is the force it takes to pull it apart. The difference between the filler wires is the type and amount of chemicals that are added to the metal. These are called deoxidizers and help clean surface oxides and gases from the molten weld, leaving small slag deposits on the finished weld bead. ER70S6 contains higher amounts of silicone and manganese. While it is a little more expensive, it does produce quality welds in different welding situations. The diameter of the filler wire is selected for the amount of the finished weld required and the deposit rate. 023 is often used with the smaller welding machines, and 030 is generally used on gauge metals. In the welding industry, 035 is considered most efficient for metals up to 3/16 of an inch. On heavier metals, 045 will provide high filler metal deposit rates. For general purpose welding, where varying amounts of weld deposit are required for different metal thicknesses, the wire size is more of a compromise. Typically, using a smaller wire like 035 and turning the welding machine up for thicker metals will give better results than using the larger 045 and trying to turn the machine down, running cold for the thinner gauge metals. The shielding gas used for welding on carbon steel is generally a blend of carbon dioxide and argon. The main job of the shielding gas is to cover the molten weld and keep it from coming in contact with oxygen and nitrogen in the surrounding air. But these gases also affect the characteristics of the arc itself. The arc creates a stream of hot, electrically charged gases. Straight carbon dioxide does not transfer current well and requires a higher voltage. A wide arc stream is formed with a lot of energy that breaks up surface oxide and allows good penetration and weld fusion. While all that arc energy does help to produce a strong weld, the problem with straight carbon dioxide is that it just isn't any fun to weld with. The high voltage and arc energy causes a harsh arc that creates more weld spatter and agitates the weld puddle, making it difficult to control. Pure argon, on the other hand, transfers current extremely well. Requiring less voltage, argon produces a narrow, dense arc stream with a secondary stream that has very little energy. On carbon steel, welds made with pure argon would penetrate in the center, but the filler metal would not fuse along the sides. What they've done is mix carbon dioxide with argon in varying amounts to provide sufficient arc energy at lower voltages. The gas blend is chosen for the amount of this arc energy it provides, and most of the argon-rich gases are used with high voltage in production welding. For some situations, because the higher argon content does reduce the energy, a little oxygen may be added just to kind of stir things up again. For general purpose all-position welding, which uses lower voltage settings, either CO2 or more commonly a blend of 75% argon and 25% CO2 provides the arc energy necessary for good weld fusion. With gas metal arc welding, when you pull the trigger on the wire feed gun, three things happen simultaneously. Circuits in the power source make current available to the wire, a solenoid opens a valve allowing the shielding gas to flow, and the drive rolls feed wire. When the wire touches the metal, the arc is started, creating the molten weld puddle. Everything works together to provide a stable transfer of filler metal from the wire to the weld puddle. One of the unique characteristics of wire feed welding is that if you want more weld deposit or more heat for better weld fusion, you simply turn the machine up. Each of these wires will operate over a wide range of voltage and wire speed settings. Throughout these ranges, though, the filler metal is transferred differently. At the lower voltage range, when the wire makes contact with the base metal, current causes the tip of the wire to heat up until it pinches off and arcs. The hot gases surrounding the arc melt the filler and the base metal, fusing them together. The continuously fed wire then overcomes the heat of the arc and contacts the metal again, heating it up, pinching it off, arcing, and fusing. This is called short circuit transfer, and the cycle happens 50 to 200 times a second, producing a distinctive sound and a weld puddle that's very easy to control. This arc on, arc off allows the molten metal to cool enough so that welds can be made in all positions: flat, horizontal, vertical, and overhead. Short circuit transfer is considered to happen at settings up to 22 volts. This voltage range and metal transfer is used for welding on thin gauge metals, ornamental type projects, and light structural. In situations where better penetration or more weld buildup is needed, the voltage and wire speed can be increased. At a certain point, around 22 volts, the wire can no longer overcome the heat of the arc, and you have an open arc. It's on all the time. Hot gases create a constant arc stream that melts the base metal. With a carbon dioxide or 75-25 shielding gas, the filler wire transfers across the arc stream in molten globs. This is called globular transfer and produces deep penetration and good filler to base metal fusion. Because of the amount of heat and weld deposit at these high settings, the molten weld puddle is extremely fluid, limiting globular transfer to the flat welding position or for a horizontal fillet. This will provide a strong weld at faster welding speeds, but the arc stream produced by CO2 or 75-25 allows some of the globs to escape, causing excessive weld spatter. For projects requiring a limited number of welds, this spatter can be dealt with, but in production it's undesirable because of the time it takes to clean up. Here's where all those different shielding gases come into play. By switching to an argon-rich gas at the higher voltage range, the dense, concentrated arc stream causes the filler metal to break up into smaller pieces. This is called spray transfer. The small pieces are sprayed across the arc stream into the molten puddle. This is the wire feed process typically used for the efficient, high-speed production welding of metals up to 3/8 of an inch thick. Here again, because of the amount of heat and weld metal, spray transfer is generally used only when the weld can be positioned flat. These methods of metal transfer throughout the wide voltage and wire speed range are what makes gas metal arc welding so versatile. We've set this machine up with some 035 ER70S6 filler wire and a 75-25 shielding gas for the all-position short circuit transfer. Let's try some welding. Just like every other type of welding, wire feed throws sparks, which are little bits of hot metal. Cover yourself up. Wear some good gloves, a hat, and always wear safety glasses. Besides hot metal sparks flying around, impurities can pop off the surface of the metal when it's heating up or cooling. Make sure the lenses in your hood are clean. Industry recommends a number 10 shaded lens. For the lower voltage ranges of short circuit welding, I use a number 9, which is a little lighter. This type of welding moves right along, and in many situations, you need to be able to see where you're going. Use clear plastic lenses to protect the shaded lens and make sure everything is sealed so that there isn't any light leaking around the edges inside the hood. Ideally, the ground clamp should be attached directly to the metal you're welding on. That's not always possible. Sometimes it's clamped to the work table, but because of the relatively low voltage, it's important to have a good, clean ground. If the wire sputters at the beginning or during the weld and the arc seems like it doesn't want to stay lit, check the ground connection. To start the weld, trim the wire so the gun can be held close to the metal. Steady yourself by using both hands on the wire feed gun with one arm supported. Move your head in close to be able to see the molten weld puddle. When you're comfortable, either reach up and slide your hood down, or you can adjust the knobs on the side to flip the hood down with a nod. Then pull the trigger. The molten puddle is controlled by the distance the gun is held from the metal, where the arc hits the puddle, the angle of the gun, and the travel speed. On the wire feed gun, the contact tip should be nearly flush with the end of the nozzle. The length of wire that sticks out from the contact tip, called electrode extension or wire stickout, will affect the amount of heat at the weld. Constant voltage power sources maintain the arc gap and provide the amperage necessary to burn off the wire. For most welds, the recommended wire stickout from the contact tip to the metal is 1/4 to 3/8 of an inch. Longer electrode extensions allow the wire to preheat, reducing the amperage necessary to burn it off and reducing the amount of heat at the weld. Holding the gun closer, which shortens the electrode extension, increases the amperage and heat for better weld fusion. The distance that the wire feed gun is held from the metal does give the welder a little more control of the heat. For good hot starts, hold the gun close to increase the amperage and heat. For thinner gauge metals or filling gaps, the gun can be pulled away a little, reducing the heat and limiting penetration. You have to be careful not to pull the gun too far away, or the weld will get too cold and may not fuse. You may even lose shielding gas coverage, causing porosity in the weld bead. For most welding situations, hold the gun close to start the weld. Then try to maintain a consistent 1/4 to 3/8 of an inch wire stickout. With the arc-on, arc-off characteristics of short-circuit transfer, there is not a lot of arc force to help drive the filler metal into the weld. For penetration and weld fusion, you want to keep the wire and the arc directed at the leading edge of the molten puddle. This is very subtle, but where the wire hits the weld puddle makes a huge difference. If the wire is directed at the back of the puddle, with molten metal floating in front of the arc, the weld buildup keeps taking the heat, not allowing the base metal to get hot enough to melt. The weld can actually float right on top without penetrating or fusing to the base metal. This is a common problem, a great looking weld that does not hold the metal together. For good weld fusion, maintain the short wire stickout and stay ahead of the weld, keeping the wire on the leading edge of the puddle. The wire feed gun can be held straight up and down, and this will put all the heat of the arc right on the base metal. Fully automatic welding processes are often set up this way, but in many fabrication situations, the nozzle gets in the way, making it difficult to see where you have to go or the weld buildup. Angle the gun slightly to provide better visibility of the molten puddle. You do want to avoid angling the gun too much. The increased wire stickout will reduce the amperage, making the weld run colder. Welds can be made in either direction, and this is another method the welder uses to control the penetration, shape, and quantity of weld. Backhand, or pulling the weld, has the gun angled back towards the weld. The heat of the arc is directed onto the molten puddle, keeping it more fluid. Generally, this will build up more weld bead, and you can watch the puddle. With forehand, or pushing the weld, the gun is angled in the direction of travel. The heat of the arc is directed away from the weld, allowing the molten puddle to cool. This tends to limit penetration, produce a flatter weld, and you get to see where you're going. With forehand, you do need to be careful to keep the wire towards the leading edge and not float too much of the puddle in front of the arc. For most welds, you can just move the gun in a straight line. A consistent wire stickout and travel speed will produce a nice looking weld with uniform penetration and weld fusion. You can also use a slight side-to-side motion, watching the outside edges of the puddle to make sure the weld is staying straight. For situations where a little more gun movement is required, a U or an upside down U will keep the arc at the front of the puddle. There are exceptions, but in wire feed, you want to avoid big wide gun movements. It makes the puddle too difficult to control. If you need more weld buildup, you can increase the wire speed and voltage to squirt more weld, or switch to a bigger wire size. For wide welds, you can also stack overlapping weld beads side by side. The speed of travel, how fast you move the gun, depends on how much heat is at the weld. You do need to move right along without hesitation to avoid excessive weld buildup, but you also have to give the arc enough time to melt the base metal, allowing the filler metal to flow out and tie in on the sides. To some extent, you can see this by watching the edge of the molten puddle. If the travel speed is too fast, the metal doesn't have time to heat up. The weld bead will just stack up on top and may not even fuse to the base metal. Traveling too slow will generally put the wire and the arc on the weld buildup, causing excessive filler metal deposit and reducing the amount of heat to the base metal. By speeding up or slowing down a little, travel speed is the main option used during the weld to control the size of the weld and ensure good weld fusion. Make sure the puddle flows out and ties in on the sides, watching the top of the puddle to avoid excessive weld buildup. One of the most important aspects for making successful welds is the voltage and wire speed settings. Basically, the voltage controls the potential amount of heat available to the weld, and the wire speed determines the amount of weld buildup. There are two parts to making the final adjustment. First, the voltage and wire speed are adjusted to provide the amount of heat and weld deposit required for the specific welding situation. Second, and this is important, the voltage and wire speed are always adjusted together to produce a stable transfer of filler metal from the welding wire into the molten puddle. This means that any time you increase the wire speed for a bigger weld, you also need to increase the voltage. The same goes that if you want a little more heat for better penetration, you can turn up the voltage, but you also need to increase the wire speed, tuning the two of them together for an optimum metal transfer. In the welding industry, wire speeds and voltage are set to produce the maximum amount of weld deposit. In smaller shops, this idea of maximum amount of weld is not always necessary or desirable, especially while you're learning to weld. A certain amount of heat is required, though, for good weld fusion. Welding charts, located on the machine or in manuals, generally reflect the minimum voltage and wire speeds for different metal thicknesses. These charts do not always take into account the position of the weld or the amount of welder skill. If you can handle the heat, you can always increase the settings for higher deposit rates and better penetration. The main purpose for the development of wire feed processes is speed. For example, if you're working with 3/16 of an inch metal, the wire speed is adjusted so that a 3/16 weld deposit can be comfortably made in one pass. As welder skill in handling the wire feed gun increases, higher wire speed settings can be used along with faster travel speeds to produce the same amount of weld in less time. Once the wire speed is set, the voltage is adjusted to produce an optimum stable filler metal transfer. The molten weld puddle should flow out to the sides and be very controllable, with the finished weld bead virtually spatter-free. If the voltage is set too high for the wire speed, the length of the arc is increased, putting more heat on the molten weld metal. The puddle is more fluid and agitated, making it difficult to control and causing excessive weld spatter. If the voltage is set too low for the wire speed, the arc length is shortened, allowing the wire to run into the puddle. The arc may be erratic, and there's not enough heat to melt both the filler metal and the base metal, so the puddle doesn't flow out on the sides. The finished weld bead will just stack up. With short circuit transfer, this optimum relationship between the wire speed and voltage can actually be adjusted by the sound of the arc. Starting with the voltage too high for the wire speed, the arc sound is erratic. As the voltage is decreased, the arc sound becomes more consistent. With the voltage too low for the wire speed, the sound becomes erratic again. The stable metal transfer is where the arc sound is most consistent. You can do this while you're welding on some practice metal, either adjusting the voltage or the wire speed if the dial on your machine is a rheostat and infinitely adjustable. If the dial clicks into ranges, you cannot change this during the weld. Regardless of where the wire speed and voltage are set, you always want to tune the two of them together to provide the optimum, nearly spatter-free metal transfer. Now, one of the biggest problems with gas metal arc welding is running too cold. Welding works best when the machine is set as hot as you can handle it. More heat produces better weld fusion and smoother weld beads. Try setting up on different metal thicknesses. Tune the voltage and wire speeds together and make some practice welds. If there's too much metal and you can't stay ahead of the puddle, turn the settings down a little. If you think you can handle a little more heat, turn them up. The final settings are determined by watching the molten puddle during the weld and examining the finished weld bead. A smooth, uniform bead will come with practice, but the edges should be fused to the base metal. If the edges are rolled over, your travel speed may be too slow, along with too low of a voltage and wire speed setting. If the weld bead stacks up, not flowing out on the sides, you might be traveling too fast, using too long of an electrode extension, or the voltage and wire speed are set too low. When there's excessive weld spatter, the voltage is probably too high for the wire speed. If the weld is kind of flattened out and all over the place, you might be running hotter than you can handle with the wire directed at the back of the puddle. When the finished weld bead has the correct size, shape, and it's fused to the base metal, that's as good as it gets. Well, that's about all there is to the fundamentals of gas metal arc welding. Have a good clean ground. Use a short electrode stick out for a hot start. Maintain a 1/4 to 3/8 wire extension for consistent penetration. Back the gun away a little to cool the puddle for filling gaps. Push the weld to limit penetration and to see where you're going. Pull the weld for more weld buildup. Set the voltage and wire speed high enough for good filler metal fusion and tune the settings for a stable metal transfer. Move slow enough to allow the puddle to flow out and tie in on the sides, but fast enough to keep the wire on the leading edge of the puddle and avoid excessive weld buildup. So far, all the demonstrations have been in the flat position. For horizontal, we'll be welding across. Because the weld buildup needs to solidify quicker so that it doesn't sag or drip, slightly angle the gun up and in the direction of travel, keeping the heat of the arc away from the molten weld buildup. Move right along with the wire at the front of the puddle and maintain a uniform travel speed and electrode stick out. If the weld bead sags, make sure you're not directing the arc back onto the puddle. Then try increasing the speed of travel to keep the base metal cooler. Vertical welds with short circuit gas metal arc welding are made downhill or downhand. Heat rises, so you'll be welding away from the heat, which keeps the base metal cooler. Angle the gun up a little using the heat of the arc to help hold the puddle up. You can either run straight down or use a slight side-to-side movement. Move fast enough to stay ahead of the molten metal, keeping the wire on the leading edge for penetration, and watching the sides to keep the weld straight. If you can't travel fast enough and stay in control, you may need to turn down the wire speed and voltage so the filler metal isn't quite so fluid. Overhead welds with wire feed, like every other welding process, are not difficult. They're just awkward. The real key to welding overhead is finding a comfortable position so that you have complete control of the wire feed gun. Angle the gun in the direction of travel to keep the heat of the arc off the weld buildup. While you're learning to weld overhead, keep moving. Don't try to build up too much weld. As you gain experience, you can carry more metal by holding the gun straighter up and down with a little side-to-side movement. If you have trouble welding overhead, make sure you're maintaining the correct wire extension and try different travel speeds. You want to go slow enough to let the puddle spread out and tie in, but fast enough to avoid overheating and excessive weld buildup. One of the advantages to wire feed is ease of operation. It won't take long for you to become comfortable running weld beads, so try practicing weld joints too. The first step is metal preparation. You absolutely have to clean any paint, rust, or grease from the metal, even the mill scale, which is the dark layer on the surface of new metal. Surface impurities will often cause little gas pockets, which is porosity, in the finished weld bead. Impurities also take the heat that should be going to the base metal, limiting weld fusion, especially at the edges, because the metal doesn't get hot enough to melt. In many situations, you'll find that it takes longer to get the metal ready to weld than it does to actually weld it. There are 4 kinds of weld joints: butt joints, lap joints, T-joints, and corner joints. Let's start with the butt joints. Extremely thin gauge metal, like auto body metal, is generally lap welded, but if your project requires a butt weld, take the time to get a perfect fit. Any gaps will cause the edges to melt away, ripping open a hole. In the flat position, push the weld to help control penetration, but if at all possible, Vertical down works best on thin gauge metals because the metal stays cooler. As the metal gets thicker, start leaving a little gap to allow for deeper welds. Keep it uniform though so you can maintain a constant travel speed. A good fit up makes it easier to produce both a good looking and strong weld joint. Ideally on butt welds, you want 100% penetration. This won't always happen, but you do want the weld deep in the joint. For maximum strength, you can always grind out the opposite side and run a weld bead for complete penetration. When the metal gets up around 1/8 of an inch thick, you can leave a little wider gap or even bevel the edges a little. Besides providing for a deeper weld, the corners of the metal heat up quickly, helping the filler metal fuse at the outside edges. If the pieces are jammed together on fit up, you can take a grinder on edge and groove the joint. On thicker metal, bevel the edges and tack the pieces together with around a 1/16 to 1/8 of an inch gap. Using a U motion, make sure the arc is directed towards the front of the puddle at the edge of the metal. Bring the wire across the gap, slightly back on the molten puddle to the front edge on the other side. Then just back and forth, keeping the arc deep in the joint. If you squirt the wire into the open gap, it will burn off, leaving cold wire in the joint. Depending on the thickness of the metal, you may not be able to fill the joint in one pass. To finish the weld, you can carry a little more metal by using a slight side-to-side motion. Keep the arc on the front edge of the weld puddle, going wide enough to cover the edges of the bevel. The idea is not to put down a whole lot more weld than you need. The amount of weld buildup should equal the thickness of the metal, but stacking filler metal on top will not do any good if the weld isn't deep in the joint. Lap joints are very simple to weld, and this is called a fillet weld. On thinner gauge metals, use a lot of tacks to keep the metal from separating. If the weld bead will be cosmetic, you can grind these tacks flush to avoid humps in the finished weld bead. Push the weld in the flat position to control penetration, or better yet, position the joint for a vertical down. On heavier metals, the weld should come up and out a distance equal to the thickness of the metal. Try holding the gun nearly perpendicular to the joint for a crown weld bead, or slightly angle the gun to push the weld for a flatter bead. Pulling the weld may cause the finished weld bead to hump up in the middle. Aim the wire into the joint. The edge of the top piece will heat up and fuse easier than the bottom, so make sure at least some of the heat of the arc is directed at the bottom piece. If the weld bead is not uniform, you may need to adjust the angle of the gun for the correct shape. The amount of weld deposit depends both on your travel speed and the wire speed setting. You can use a slight gun movement to carry more metal, but if you can handle the heat, increase the voltage and wire speed to deposit more filler metal. A fillet weld is also used for T-joints, and this is very similar to a lap weld. Vertical down fillets on thinner metal seems to produce the nicest looking weld, but if there is a drawback to the gas metal arc welding process, it is vertical down welds on thicker metal. A higher voltage is necessary to ensure good weld fusion. To keep a stable metal transfer, that also means a faster wire speed, to the point where you may not be able to handle the quantity of molten weld coming down. You can make these welds by running hot with a faster travel speed to prevent excessive weld buildup, then multi-passing to increase the size of the weld. Corner joints are fit up several ways. The edges can be lapped with a weld bead on the outside edge. For thin gauge metal, try to position the joint for a vertical down. On thicker metals, bevel or grind a groove on one edge. If you're concerned at all about the strength of the joint, a fillet weld can also be added to the inside, but this will tend to draw the pieces in the direction of the fillet. Corners can also be fit up by lining up the inside edges, more or less forming a bevel. Try leaving a little gap for complete penetration. This type of corner provides a good-looking, strong weld joint that's easy to weld. Practice these different weld joints. Watch the molten puddle. Examine the finished weld bead, and even try breaking the welds to see if the filler metal is fusing to the base metal. A big part of learning to weld is figuring out what works for you. We've been demonstrating all position welding and weld joints with the low voltage range short circuit metal transfer. For faster deposit rates or better penetration, using the same filler wire, you can turn up the voltage and wire speed. Over 22 volts, you'll have an open arc and globular transfer with carbon dioxide or 75-25, or spray transfer with an argon-rich gas. From the welder's point of view, these are similar, and while it is high-speed welding, it's also very simple. Because of the amount of heat in filler metal, these are generally used only in the flat position or for a horizontal fillet, which is basically flat. The contact tip should be slightly recessed and use a longer electrode extension, around a ½ inch. Angle the gun slightly to push the weld, directing some of the heat away from the molten metal. Aim the wire into the joint, pull the trigger, and try to stay ahead of the weld buildup. When you stop, examine the finished weld. You may need to adjust the travel speed and the gun angle for proper weld deposit. With the higher voltage open arc, you can no longer use the sound to adjust the voltage and wire speed settings, but they still need to be tuned together. The wire speed is set to provide the required amount of weld. On machines like this, the dial indicates a percentage of the maximum wire speed, which is generally around 700 inches per minute. Each increment represents 70 inches per minute of wire. For 035 wire, start with a minimum of 420 inches per minute. The voltage setting, starting around 25 volts, will vary depending on the shielding gas blend. The voltage regulates the actual arc length, so if the volts are set too high, the arc gap will be long, throwing heat on the molten puddle and making it difficult to control. If the voltage is set too low, the wire runs into the puddle, kind of exploding and causing excessive weld spatter. Adjust the voltage to obtain a short arc length. Globular transfer with carbon dioxide or 75-25 will produce weld spatter. You really can't get away from it. Spray transfer with an argon-rich gas and the wire speed and voltage tuned for a short arc length will produce a nearly spatter-free weld. Either globular or spray can be used on any metal thickness that can handle that amount of heat. In industry, though, spray transfer is considered most efficient for metals up to 3/8 of an inch thick. Other welding processes are used for thicker metal to provide even more weld deposit and faster welding speeds. Well, that's about it. I hope I've given you an idea of what to do and what to look for. Wire feed welding is all about putting down the required amount of weld with good filler metal fusion. The size of the weld is controlled by the wire speed setting and travel speed. The heat at the weld is determined by the voltage, travel speed, and electrode extension. Become familiar with your equipment and maintain it to keep the wire feeding smoothly. Clean the metal and take the time for a good joint fit up. Practice the welds and weld joints in different positions. Always tune the voltage and wire speed for a stable metal transfer. Keep the wire on the leading edge of the puddle for penetration, watching the sides and the weld build up. Above all else, have fun with this and work safely.